Okay, in this video, I will talk about the work done by some special cases, which are conservative forces. So work by conservative forces. Okay, so we'll talk about the definition, and then later on we will show you some example of this force calculation, the work calculation. Okay, so what are conservative forces? Okay, the definition is the following. If it satisfies either one of the following condition, then this force can be called conservative force. Okay, so the definition is that the first one is the work by a force does not depend on the path between the initial and final position. Then such a force is, if we satisfy this condition, then such a force is a conservative force. Now here is the picture to show you this definition. So let's say there's a initial and final position. Okay. Now let's say an object move between these 2 points, and it can move in a straight line. Okay, so let's call this path A. Okay, and it can also move along this curved path. That's the path B. But even like other different curves, path C, maybe here from below, it's D. Okay. In fact, you can draw infinite number of such paths. Okay, but in all these cases, okay, there's a force acting on this object, and the work done by such a force, which is defined as force dot ds integral from initial to final, right? And if you do this integral along path A, then you have A, WFA. Now it turns out that this WFA equals WFB equals WFC equals all these different passes value. Okay, work in along all these different passes, they have exactly the same value. Then we say F is a conservative force. Okay, so in terms of how to prove such a force is a conservative force, we need to calculate this work along different passes, and then we need to show that they're the same. Now the second condition, or if the force satisfies the second condition, then it's called also a conservative force. Okay, so what is this definition? The definition is that in the second condition is that if the work done by such a force in a closed loop is 0. Okay, if the force satisfies such a condition, then we can also say such a force is conservative. Okay, now again, I want to represent this in a picture. Here is the initial position. Okay, and the object will go around and along any path and then go back to the same location. So initial position is also the final position. They're at the same location. Okay. And the work done by a force F along such a closed path is 0. Then we say such a force is conservative force. Okay, so these are just definition. So now let's think about some specific forces that can be called conservative force and how we can calculate work done by such a force. Okay, now the first come into mind is the gravity work. Let's think about work done by gravity. Okay, now to facilitate our calculation, I want to build this coordinate system, and I'm assuming that an object is doing a two-dimensional motion. Okay, and it's not necessarily limited to the two-dimensional. It's just that this case can be general, but at the same time, I just need to think about two components of the position coordinate system. Okay. Now here's an object, and that's the initial position, and we want to move this object to another location here, final position. Okay, and it can be some arbitrary path, and let me pick one of them through such a path. Okay. Now, of course, correspond to the initial position as this y initial, x initial, y final, x final. We have all these coordinates that we know. Now we want to calculate the work done by gravity, okay, in this process. Now according to the definition is Fg dot ds integral from initial to final position. Okay. Now let's take one point in the somewhere in the process, and let's address this point as the arbitrary point, and then later on we should be able to plug in our formula and do the calculation. Okay. So at this intermediate point, we draw the free body diagram. The work is the gravity is downward, okay, which is Fg equals mg. And I want to rewrite this as a vector form, so I need to use the j hat. Okay, so j hat, remember, is the unit vector along the y-axis. So here's negative j hat. Okay, now the ds here is along the tangential direction of the path. So let's say that's the ds. Okay. All right. So now we have that. Let's put in here initial to final, and Fg is given by mg negative j hat dot ds. Okay. However, in order to further this calculation, I need to do more thing here. I need to also write down the this ds in a component form. And to do that, I want to move this ds away so that you can see this clearly. So that's ds, right? So we want, and if I decompose these into two directions, there I have dx and dy. Okay, and in this case here, dx here is positive, pointing to the right, right? And I should add the I hat here, And dy in this case is negative, right, because it's downward. And the unit here is still, unit vector here is still j hat. It's just that dy, this quantity becomes negative. It's downward. And that's what I need. So I want to replace ds by dx I hat plus dy j hat. Okay. Now when I do this dot product, I can distribute this term j hat to do dot product with these two different terms. Okay, so we had j hat dot I hat. So let's talk about this j hat dot I hat. Okay, and it's given by the magnitude of j hat is 1, magnitude of j of I hat is 1. The angle between them is 90 degrees. So we get 0 here. Now if I do j hat dot j hat, I get also 1 times cosine 0 degree. So I get 1 here. So if I distribute this term into the two terms, then the first term here is 0. Second term, j hat dot j hat is 1. Okay, now to summarize, work done by gravity equals I to F negative mg dy. Now since the x dependence now disappear, right? Because there's no x here in the integration. So you can say this I hat now is just y, this I position just yi, and this f index is just y, yf. The integral here gives us negative mg y final minus y initial. Okay, so now we see there's no memory about what kind of path that we draw between point I and point F. The path could be this one as well, and we will have exactly the same calculation, right? So that's why this result here is independent of path. Okay, and it only depends on the initial and final position. Okay, so that's why we can say we proved this already, because the work here does not depend on the actual path taken to go from initial to final position. So that's why the force Fg here is a conservative force. Okay, let's also summarize the work done by gravity is given by this expression. Okay, it's always given by that expression. And in the future, we're going to use this calculation here, the result here, to define the potential energy. Okay, so it forms the basis of potential energy definition. We'll see that in the next chapter. All right, so gravity is one conservative force example. The other conservative force example is the spring force. So the work done by spring force. How do we do that calculation? Now here's the setup. There's the let's say a spring sitting on attached to an object and is sitting on the ground. Okay, so here's spring, and it has a constant K, spring constant K, attached to this wall. There's mass M that can be stretched, can be pulled, so that the spring can be pulled to some position, and then we will let go, and it will do oscillation. Okay, so now let's say right now is the length of the spring is the original length of spring. Let's call it L naught, Now when I pull this spring to this new position, then the spring is stretched, right? And then there will be a force generated by the spring acting on the mass m. So think about that force. So I'm going to use this dashed line here, okay, to represent the original length of the spring. And right at this location, there's no spring force. Okay, but now I want to use this position as the origin. This dashed line here, this level is the origin, and then build a coordinate system this way. That's the x-axis. Okay, so right now the object's position is at x. Okay, then there's a spring force equals negative kx. Okay, so I add the negative sign here to represent the direction of the force, right? Because right now the spring force is this way. It's F spring pointing along the negative x-axis. Okay, so if this x is positive, then the spring force is negative, meaning it's pointing to the left side. Now let's look at another situation where we have a positive force. Now here's the spring system again, and the object now is compressed. The spring now is compressed. The object is pushed to the left side of the origin. Okay, so now it still has position x, but we should remember that this x here is negative. Okay, now the spring force should be resisting this push, right? This compression. So the spring force will be this way. And you can see when I write down the spring force expression, it's still this expression here, still this negative kx, where x is negative and spring force is positive. Okay, so that is you can say a general relation between spring force and the displacement of the spring, and we can use that to do some calculation of the work. Remember, our purpose here is doing calculation on the work, so we need some expression. Now we're going to do that just like in the case of the gravitational force calculation. I want to assume some initial and some final position. Okay, so let's see how we can do this integral here. We need to do the work done by spring by doing this integral f spring dot ds integral from initial to the final position. All right, so now since I already figured out this expression, right, so I just want to change this expression into a vector form by adding this I hat. Okay, so that's what we plug in here. So negative kx I hat is going to dot product ds. Now ds here, since it's a one-dimensional vector, right? So ds is simply just the x I hat. Okay, so that's what will come in here, the x I hat. Okay, so in this sense, we are doing just one-dimensional dot product, so it's easier than the gravitational force case. Okay. All right, so now we have from xi to x final. Now let's continue here. The work done, so spring equals I hat dot I hat equals 1, right? It's these two terms. And then we get rid of the dot product, and then we have negative kx dx from xi to x final. Okay, so that gives us negative 1/2 k x squared, and x goes from initial to final. Now if I plug in the lower and upper bounds, I get negative 1/2 k x final squared minus x initial squared. Okay, so that's the work done by the spring force in this case. And we also see this example as how to do calculation for a lying force, a force that is changing its magnitude and also direction, okay, as an example of that. Okay, unlike the gravity, right? Gravity is a constant force. All right, so now we have the expression for the work done by the spring force, and we can see that again it's independent of the path. Okay, so we can apply this result to any path we take. You may ask me, what do I mean by different paths, right? Isn't that just one path, right? So the object moved from this xi to x final, right? Just this displacement. The answer is that there could be some other paths. So let me show you. So let's say right now the object moving this way, right? And then reach the final position, okay? But it doesn't stop, right? So for the spring system, it can oscillate. So it can overshoot this position. That's like path A. Now overshoot this position, go to the maximum compression, and then go back. And that would be like path B, okay? But it can also, you can call this final position, but it can also like overshoot this position, go back to the oscillation, and then going back again, second time, okay? Third time. Then we call this path C, but that's not the only path we have. The only three paths we have, we can still overshoot this and then go back here, and then that will be D, and then later on go oscillation again, then we have E, right, etc. So we have infinite number of paths. So that's why the result for all these oscillations, all these different paths, the result for the work done by the spring force is always the same. Okay, so that's why the spring force is a conservative force. And again, in the future, we talk about the potential energy. We'll define the potential energy using this result. Okay, so the work done by spring is given by this useful expression. Okay, so in the remaining of the chapter, I want to just define briefly the power, physical quantity power. Okay, so power is defined as the work done in unit time. So power is work in unit time. Okay, so let's look at this definition. So let's say in time delta t, in time interval delta t, there's a force does work W, okay, delta W on an object. Then we should define this power. The power symbol is P, okay, and in this case, it's average power equals delta W over delta T, okay. And in some other cases, you can say if I take the limit of delta T goes to 0, then of course we have some instantaneous power equals dW dt. Okay, but you can also define the power as the energy change, okay, because the work done on an object has a relation with the energy change of the object, and usually they're equal, so that's why we can say delta E over delta T. Okay. All right, so if you say a work done on an object speeds up, then its kinetic energy increases. The increase of the kinetic energy equals the amount of work done on the object. Okay, so we'll talk about all that in the future. But again, here's the definition of the power. Power is work in unit time. Okay, that's all for this video. Thanks for watching.